Alright, good morning ladies and gentlemen. It is Tuesday, April the 7th, 2020, and we are going to finish our lesson about absolute value functions and their graphs, as this says at the top, absolute value function graph. And let's move on. So, when we graph absolute value functions, we want to see how they are compared to other graphs. Like if this is just our base absolute value function, you can tell it's the base because it's just the absolute value bars and nothing else. We want to compare that to this. Now, take a moment, just think about, alright, what type of function is that? It's definitely not linear, it's not a radical, it's not an exponential, it is a quadratic because of that second power. It's also technically a polynomial. So, we want to be able to graph these, and we want to see where do they intersect, because oftentimes in algebra they ask us, alright, what is the value of x that makes both of these two the same? Luckily, I kind of took this one as a little easier approach. I've got an intersection here, and I've got an intersection here. Now, for a lot of you guys, especially during class, we would talk about, okay, what's more important when it comes to intersections? Do I care about this x-axis, or do I care about the y-axis? Mr. K, you're supposed to care about both axes, or axes, however you want to pronounce it. Yes, that is true, but when it comes to intersections, remember, I'm looking for an x value. Therefore, I should be looking on an x-axis. I want to be able to find out where are these points. You could eyeball this one. You could also try to do a little bit of guessing and checking. It's probably not an efficient method to just guess and check, but definitely I want to emphasize, well actually let's do find that out since that is part of our problem. If I have an negative x squared plus 6, I know that this has to be this quadratic that's going down at these 2 points. And my absolute value has to be this bar, this light purple, if you could tell, because there's a certain point where it kind of bounces off the x-axis and goes up linearly besides that. Now, if I wanted to see x is equal to 2, Mr. K, how do you know that? Well, if I say that x is equal to either negative 2 or positive 2 here, what's 2 squared? Well, 2 squared is 4, right? Well, negative 4 plus 6 gives you 2. And obviously, when you plug in 2 for that, you get 2 as well. So that is at 2 and negative 2. Now that lesson kind of got away from me because what I was really trying to emphasize are the shapes of these graphs. We know the quadratic is the one that makes this parabola, where it kind of has a maximum here, a maximum or a minimum, that vertex, where it is either the highest or the lowest point of your parabola, and then it kind of cascades from there, where it just drops off, or would either be rising from there. That's definitely a quadratic, and my students should know what that is. Which means this other graph has to be our absolute value. Now, this V shape that it makes is super funny. Like, hey, it comes to a point, then it immediately bounces back off and goes the other direction. Well, that's because this x value, or technically the y value when you're plugging in values for x, for this one can't have a negative value. Because remember from yesterday, if you put a negative value into there, it's going to become a positive value. So even if you put in a negative 2, well, negative 2, which would have been down here, is now a positive 2, because it takes that absolute value and it switches it to the other side. let's move on. Now, check for understanding. I would want you guys to pause and actually draw these, but it might be kind of hard to draw on a video, so I'm going to do the drawing. Now, once again, just pause, see if you can do it on your own. But we want to see if we can draw these rough sketches. That first one, super easy. I'm going to start with my y-intercept. I'm going to go down to 1, 2, 3, 4. Now, remember, when you're drawing things, it's good to be in the right ballpark, but it doesn't have to be exact. If I can tell what you're doing, if someone could tell what you're drawing or what you're graphing, you've done it correct. Now, my y-intercept was this -4. And so I go down to -4 down here, boom, y-intercept. Now, I also have a slope of a -3x, which means it goes down 3 for every time it goes over 1. Because that's technically a -3 over 1, right? Because if you divide anything by 1, it doesn't change anything. So if I wanted to graph this, I'd go 1, 2, 3, 1. Alright, that's a point there. Now if I want to go the opposite way, it's going to do the opposite thing. I'm going to go up 3 and over 1, up 3 over 1, up 3 over 1. So 1, 2, 3 over 1. 1, 2, 3 over 1, and so on and so forth. So I'm actually impressed with that. Wasn't the worst graph that I've ever done. But let's switch colors. Let's switch something to represent Manassas. Let's represent Manassas with some blue. There we go. And remember, I need to have an absolute value. So it's going to make that V shape. Now, since this is a +2 out in front, the V is still going to be pointed upwards, or the V is going to open upwards. But do remember, I've got a y-intercept of a -3. So I'm going to be right about there. And instead of going up 1 and over 1, this is going to go up 2 and over 1. Because remember, this is still 2 technically over 1. Gosh, I keep losing my mouse. Where's my mouse? There we go. Up 2. And so they technically meet, they intersect right here. Now this is an interesting one. This graph appears to only intersect once, and it's totally fine. You might not have 2 intersections. You might only have 1 intersection, depending on how your graph is built or how your function is built. Now, do you know where that intersection is? And intersection, obviously being right there, appears to be at -1. X is equal to a -1, and y is equal to a -1 as well. Interesting. Let me go back to my normal pen color. So, this appears to only have 1 intersection, which is good. If I plug in a -1 into here, what's -1 times a -3? Well, that's a +3. What's +3 minus 1? +3 minus 4 gives you a -1. What's a -1 absolute value? +1. What's +1 times 2? 2. What's 2 minus 3? -1. Awesome. Now, not all these will be super easy to be able to either build or to identify. Always do what you can. If you can't get it on your own, don't be afraid to grab a calculator or anything. But what's important right now is I want you guys to understand what these two graph shapes look like. Absolute values always look like, let me see, V's. Linears are always straight lines. Quadratics are the parabolas. So, V for absolute value line for linear. And quadratics have the loop because they're just silly quadratics. All right, moving on. I want us to be able to compare some absolute value functions to other functions. Kind of like what we just did, but a little bit more in depth. Distinctly, I want us to be able to find these intersections. So, first and foremost, which graph is which? If you listen to the last part, you should be able to tell that, hey, this blue one looks like a V, so this has to be my first function. It's my absolute value, and you'd be correct, meaning this has to be my second. Now, if you look at these graphs, you might say, oh hey, Mr. K, this is obviously my origin, so they have to intersect at x is equal to 0. That's really good intuition. If you can tell that, hey, that is your origin, and they intersect somewhere at the origin, they intersect at this intercept, well, neat. But let's always double check this, because you never know when you might be slightly off. Alright, if I plug in 0, what's 0 plus 4? 0 plus 4 minus 2, or obviously let's put in our absolute values. Well, that's going to be the same thing as 4 minus 2. Well, it's 2. Now if I put 0 in here, what's 0 plus 6? 6 divided by 3. Gosh, that is an ugly looking 3. That is even worse. I am going to take the time to erase that. Alright. Ladies and gentlemen, that never happened. 2. So, x is equal to 0, y is equal to 2 is definitely one of our intersections. That's pretty good. You might say, oh, Mr. K, that's just 1, 2, 3 steps over. The other one obviously has to be a negative 3. But boys and girls, be careful. Not all your graphs are drawn to scale. Just because these look like they're 3 individual steps doesn't mean they're 3 steps. Let's plug in a negative 3 and let's see what we get. First one is a negative 3 plus 4 minus 2. Well, that's going to be positive 1 minus 2. That would give me a negative 1. And this is a 0, not negative 1. So we know it can't really be a negative 3. So negative 3 is already off the table. Let's see what else it could possibly be. Well, since this is at y is equal to 0, what are going to make these equations equal to 0? Specifically, this one. Well, if I'm going to make x plus 6 divided by 3 equal to 0, the only way I can really see that is if my numerator is equal to 0, because that's the only thing changing. So what plus 6 gives me 0? What if x is negative 6? Well, if x is negative 6, that's negative 6 plus 6, which would give me 0 over 3. Minerva girl, come here. Come here. My cat's being a little bit noisy, but we love her just the same. Oh, Nazgul wants to come over as well. She's starting to fight me a little bit. Oh, look at this little beauty. She wants some attention. Anyways, alright, sit with me. Still go do my lesson. Alright, so, that's definitely equal to 0. That's good. But how are we going to make the other one equal to 0? Well, let's do some opposite operations. X plus 4 is equal to a positive 2. Mr. K, how'd you get that? Well, I just added 2 to both sides. Well, that means x plus 4 is equal to a positive 2, but it's also equal to x plus 4 is equal to a negative 2. Now, when it comes to x plus 4 is equal to a positive 2, I want... She's having some fun with some stuff back there. I want to be able to figure out when I'm going to get to a 0. So I need a negative value, not a positive value. So I'm going to skip that one and say, alright, x is equal to a negative 6. Well, that looks like it's going to get me a 0. And if I say that's a negative 6 and that's a negative 6, my two solutions are x is equal to negative 6 and x is equal to 0. Alright, let's wrap this up. What are the intersections for these two functions? Well, that is super interesting, super neat. Once again, we might not be able to eyeball this one. We want to be able to see, alright, where is this x value? And where is this one? Take some time, pause the video, try to work it out using logic. Whatever it has to be is that the x's have to be the same for both these equations. Meaning, if you plug in the same x value into this one, or the same x value into that value, and the same x value into that value, you have to get the same answer. And your answers should be a positive 1 and a positive 5. And if we see that, let's just test one of them. If I plug in a positive 1, now let's do 5. 5 is going to be easier. Alright, if I plug in 5 into this, 5 minus 2 is 3, right? What's 3 times a negative 2? Well, 3 times a negative 2 is a negative 6. What's a negative 5, because remember you've got a negative sign there, minus 1? Negative 6. 5 works. Alright, try out the x is equal to 1, see what you can do with it. Ladies and gentlemen, also just to remind you, you have an assignment in Microsoft Teams. If you need any help getting into Microsoft Teams, you've got to email me. You can email me at my website, Kreitlein, this is really not good, Kreitlein Math .weebly.com. Alright, ladies and gentlemen, hope you have yourselves a good Tuesday. May your Tuesdays be filled with tacos. Tacos are delicious. And have a nice day.